Good afternoon, and welcome to the third and the last paper session of the day. We will start in a minute, and this session is called Sensing Applications. It has three extraordinary papers that is touching three different dimensions of new sensing applications, ranging from spiking detections to vibration sensing, and finally we'll talk about how to detect blood pressure using wearable sensors. So three exciting papers, and my name is Nirupam Roy, and this is the guy who spammed you for the last couple of months with lots of emails and asking for letters, this and that. So now you know who I am, and you can find me to give a piece of your mind, if you like to. So I'm from University of Maryland. I work on IoT, acoustic, intelligent acoustic systems. And today I am going to chair, I'm honored to chair this session. We'll start with the paper that's called Hedgehog, Detecting Drink Spiking on Wearables, a really, really timely and difficult challenge to solve. The lead author of this paper is Jigang In. He is a doctoral candidate at the University of Tartu, Estonia. His research interests are in light sensing, autonomous vehicles, and pervasive systems. Unfortunately, he could not be here to present because of the visa issues, and Mohan has kindly taken up the challenge to present on his behalf. Mohan is one of the faculty members at the same university. Without further delay, I will let Mohan to raise the stage. So please put your hand together for Mohan.
Okay, good afternoon. So I'm Mohan Lianage from the University of Tartu in Estonia. So I am here to present our work, Hedgehog. So as Niro mentioned, Xinjiang is the main contributor, but unfortunately he couldn't come here. So if you think about the social context, so drink spiking is some type of a critical issue. So mainly the idea is somebody can put some drug type of compounds into someone's drink without their consent. So the problem is it's actually a critical social issue because the victim, it may be is in a severe danger, and also the idea of the thing is like once if your drink is spiked, so the victim can be more vulnerable to assault. So in that sense, we need to find out. So it's very important to find out so whether your drink is spiked or not. So when we talk about the current solutions, the mainly some sort of guidelines and also some advices we can see. So that the idea is, for example, in this some of the research showing that at least around 8% of college students had the drink spike experience. So we can produce or we can give them some sort of advice. Okay, for example, in the social gathering, don't leave your drink unattended, or maybe always keep on an eye on your drink, or maybe sometimes you can ask seal product. So, but like it's happening like during the social gathering, it's very difficult to follow those guidelines. And also another thing, most of the times the people, they actually underestimate the risk of this spiking. So sometimes they may be not follow those guidelines. And we can see another solution like using a specialized utensils. For example, maybe special type of cups or maybe straws. So if they can change their color if your drink spike with some sort of drugs. But again, this is also a problem like that may be only for like particular drugs. And you can see if you search, you can see there are some like type of solutions available in that regard. Also, it is possible if we can take a sample of a drink and you can do the lab testing, right? But so those solutions actually we cannot easily apply during that social gathering. So then we need to a solution like maybe a simple to use and also you can easily deploy in this social gatherings. So in this regard, so this is our work, Hedgehog. So the main or primary idea behind is how we reuse our wearables and especially this light sensors in these wearables to find out the spike drinks. So with a lot of benchmark testings, and we can demonstrate that it is feasible or it is easy and to find out, okay, so this is your drink and then it may be contaminated with something else. Right? But the main problem is like here it can identify okay, whether your drink is spiked or not, but keep in mind we cannot say exactly the chemical component. For example, your drink is spiked with that drug or maybe this drug, right? But this is actually we need more data to find out this type of issues. But right now we can say, okay, your drink is now tampered with something else. So this is the complete overview of this model. So you can see there we use the smart ring. So most of the times this light sensor is actually inside. So because that sensor touches your skin and maybe getting some sort of data, for example, heart rate or maybe blood pressure, so on. But in our case, we need to put it on the exterior surface, because once you hold your drink or your glass, so this light sensor can just sense your drink or this glass. And as you know, this light beam is actually can travel through the drink, but some portion of this beam can be reflected and refracted. So we can use that reflected waves and rays, and then we can measure, okay, how much of how about the values of that reflected rays, and with that we can make a profile for that drink. So this profile is actually we trying to use if it is actually spiked with some sort of compound. So then the light profile is actually differs from the initial one. So that is the concept behind that. So we see using that we can see, okay, we can find out this spike. So and the next in this figure C, you can see it's possibly we can wear like maybe your middle finger or index finger anywhere, right? So in this experiment, so we also tested with those 3 locations mainly. And the last one at the corner, you can see this is the normal the sensing pipeline. So we collect this reflection data and then noise removal and then send to the classification. So here you can see the test bed. This number 1, you can see how it's really working. So we made the prototype with M5 C stack. It's a small prototype board with a micro controller, and it has also the Wi-Fi connectivity. So easily we can connect, we can send your data to, for example, your mobile phone or maybe a local server to process. And this prototype board actually is connected with the small light sensor. It has a light and also a photoreceptor. So, and we are using, here you can see we have 3 different drinks and also some medicines. And at the end, you can see we have 3 different type of glasses also with different drinks. So here idea is to get the generalized system. So we have to try, okay, for example, it may be during the social that, for example, in the party. So it's time to time, it may be different. For example, you may have like a white or plain glass, or maybe next time it may be like some colored one. So then we need to get that generalized model. So we need more data. So we had like here quite a lot experiments to get that model. So this is the evaluation part. Here you can see at the very beginning, so we had this experiments with these 3 different locations and with 6 type of drinks. So there you can see easily we can find out, okay, the profiles are actually different. And even with this both, like all the 3 locations, we can get the different profiles. And the next one is, how about the concentration? For example, the drink may be contaminated with a very small amount of drug or maybe a bit stronger or more content. So to analyze that feasibility, also we had the same type of experiment, but here 3 different locations, but with different concentrations. So there also you can see the Hedgehog can identify with this different concentrations. And how we can, if we think about this classification performance. So here you can see the baseline is just water, and then we have 3 different medicines spiked with this with water. So here when we check about the classification performance, so we can see the middle finger is actually the best position to find out the or get this proper profile of the drink. So the reason is, for example, if it is the small finger, so when you grab the glass, so there may be, it's actually depending on the force, like how strong you grab the glass. And then if it is a small finger, sometimes it's not properly touch the glass. And then there may be a gap, small gap in between glass and the sensor. So maybe the external, maybe ambient light maybe touches the sensor. So then you cannot get the proper values. So after this experiment, so we only consider the middle finger is the best place. So and then we only consider the readings from this location. Okay, and there's another aspect. For example, if this drug is not like not properly soluble. For example, there are some drugs. Here we use aspirin, but it's highly soluble one, not the normal aspirin. So then, once you put a small amount, it's like quickly it's dissolved. But some drugs, it's actually dissolving very slowly. And during that time, if you spike that drug with the drink, so it's taking like sometimes, and then if you examine very closely, there's some particles actually going from top to the bottom. So during that time, if you just check your drink, sometimes you are getting the false positives. Or maybe it may be saying, okay, it's not spiked, but actually it's already has been spiked, right? So to understand that scenario, so we design another like test case. So here you can see S, that's saying spiked, and SN mean, so we spike the drink and keep it for an hour, right? And then we test the drink. So then the third case, actually, we spike the drink after an hour, so we shake the drink. So their idea is like, if there are some particles still there, so once you shake it, you can see it's spiked. And here you can see there are three different medicines. For example, if you check this, the last column, the water with Mirzapan, so here you can see it's like a very close result for even all three cases. So the idea is, because this medicine, it has a kind of it's colored medicine. I don't remember, it's like brown or something. So then anyway, like once it is added to that medicine, that drink, anyway the color is changed, then you can find out it. Right? But in some other cases, we have to analyze, okay, how about the timing also dealing with this process. So the practicability. So in the social gathering, like in the parties, so we have different light settings, right? So you may be sitting here, and then after that you move to somewhere else, right? So then the light settings may be completely different. So to identify how that light, ambient light settings or the luminosity is affected, so again we have that test case. So here we use three different locations or light settings: indoor arboreal light, and then the completely dark, and outdoor ambient light. And at the same time, three different type of cups. So with that results, and here you can see baseline and then two medicines. Again, we applied there. And with that results, here you can see the ambient light is actually not that much affected to the classification performance. So that's mean this Hedgehog can actually identify whether your drink is tampered with the compounds or not. Okay, so ongoing work to get, okay, the thing is like here main point is getting the profile of this link. So here we can, if it is like going to like to generalize, so we need more data. So how we can collect that data? So we can ask this crowd sensing approaches, right? We can move to that approach. And then, for example, if you have a drink, then if you can send or the profile of the link, for example, with the type of the glass or the what is the brand of the beer, for example, and the color, something like that. So with the so that sort of data, so we can actually generalize this model. And the theoretical model here actually, so how we use this refraction or reflection, and then because some drinks, for example, if it is a water, so then the most of the light actually going through the water, right? But if it's a dark beer, so then heavy reflection is there. So then with different liquids, so we need actually sort of sophisticated model to get the better idea. And this is the summary and conclusion. So we have a pervasive sensing approach, and then how we use the already off-the-shelf wearables to identify ring spiking. Okay, and I should thanks to this European Social Fund and the Academy of Finland and Nokia grant, so who actually contribute to get that project, right? And yeah, thank you for listening, and I am happy to answer your questions. And this is our lab. You can reach us, you can write us if you need more details. Thank you.
Thank you, Mohan. Questions?
thank you for the presentation. So I kind of missed the beginning of the presentation. Sorry, I was in the poster side. So you inject some sort of light, and you have also the detector in the same hand, right?
Yeah, photoresist.
Okay.
Yeah.
What if you had some sort of like a base where the consumer puts the drink on the base, and there is a light coming from the bottom of the drink, for example? Would that be an alternative solution?
What do you mean, like a because here the idea is we use the already that the for example, like a smart ring. So then it's not like only for this purpose. So we are actually repurposing or reusing the already available technology.
Okay.
So, but your question is like if you put
maybe some other way to make the application. So instead of wearing something at the bar or whatever, you have something on the table where somebody can place the drink and see if it is spiked as a...
Yeah, that's also possible. But if you check our paper, we had also the same arrangement. Like we use this Samsung Smart watch, and then it's actually we put it just on top of
Does
and
it
then
work?
it can read this data. But this is actually the idea is it can easily detect like if you have some sediment like at the bottom, right? But if it is fully soluble, so then it has some drawbacks.
Okay, I see. Yeah. Okay, thank you.
Thanks. Really interesting work, actually, on a really important problem. I might fleetingly just respond to the other question, which is a lot of the times when people have done this in the past, that the problem is in practice, no one thinks to go and put their drink on a stand every 30 seconds to see if someone's dropped something in it. So you really do want something in your hand. But two questions. You may have mentioned it, I missed it. Did you have ice in the drinks? Did you have any kind of solids in the drink, ice or, fruit or anything else? Or was it just a clear liquid?
But do you mean like if it's a solid one, then or it's fully dissolved one, or?
I think I was trying to work out whether the system still worked if you'd got, for example, a lot of ice in with the drink.
Yeah. So you only the thing is like you just hold it for example 30 seconds. So then during that time we can read we can generate the profile for that drink. So.
Sorry, yeah, I had the same question, but ice or something like that would dilute the drink over time. So if you're looking at it like 30 minutes later, it would be a different.
Yeah, that's
of course.
The natural state would be different.
Yeah. So in that case, we need like more data. For example, here we tested like mainly beer and some soft drinks. For example, if it is a cocktail, so then at the very beginning you have some maybe ice cubes and then something, and then that time the link profile is actually completely changes over times, and for example after 30 minutes, right? But that's why we use here displays. So, but the here idea is completely dissolved, or maybe some sediment actually at the bottom. So then there we can find out easily. Then you need to shake it. But in that case, like for example, if it is a cocktail, we cannot right now we cannot directly get the use of this method, right? But if we have more profiles, for example, cocktail with those ingredients, or then it can be, yeah.
Okay, all right, thank you.
Interesting work. I wanted to kind of refer you to another piece of work from IBM research called Crypto Anchor Verifier, where they used a general smartphone and attached some optical lens to it to study the spectral properties of the fluid, and were able to kind of detect between olive oil and adulterated olive oil, or motor oil that's adulterated, and things like that.
Okay.
This might be worthwhile for you to look it up.
Yeah, exactly. Thank you for knowing us.
I have a quick question. I actually had the same question about ice, but also this slide. Do you have a sense of why SN and SS sort of differ, and the pattern is also different for different solubles. Because ideally, I would expect that SS would go down over time, and SN would be similar to S.
SN and because here the idea is, for example, if it is a normal paracetamol, so now you are reading your drink, like get your first the fingerprint, and then once you just drop, then very small amount of paracetamol, and it's also depending on that. For example, the location, here you can see this the figure D. So your ring is there, just like for example saying like 5 centimeters from the top, right? So if you add that type of drug, so if it is a quickly dissolved and then easily the right away, for example, after 10 seconds, you can see the difference. But if it is slowly, like coming from top to bottom, so during that time, sometimes may say, okay, it's not spiked, but it's already spiked there, right? So that's why we have that differences, and also it's completely depending on the type of compound what we applied here. So we need like a model. Actually, it's also one of our ongoing work to generalize the model, that sort of particles, how it's taking from from top to bottom when it is traveling, how we can generate this fingerprints.
Awesome. Thank you. Very cool
Welcome.
work.
Thank you. Let's thank the speaker once again.
Okay.